Good morning everyone. Today I would like to talk about my topic research or the low temperature proton exchange membrane fuel cell for unmanned aerial vehicles or UAV. My name is Natthakorn and my student ID is 608445007. My advisor is Professor Yong Song Chen. So today I would like to talk about my topic or my research. So let's move on to the outline. In the outline, I already divided into the four parts. The first one is a part of introductions. In the part of introductions, I will introduce you what is a fuel cell and how it working. And the next one is a part of the experimental. So I will talk about the method or methodology that I using, and I will example some method or some machines to you, and then I will talk about my results and discussion it in on after the results, and I will conclude everything in a part of conclusions. So let me move on to the part of introductions. What is a fuel cell? The fuel cell is an electrochemical device which combines with hydrogen and oxygen to produce the electricity by heat and water as generated or as a byproduct. So we will put the hydrogen here and oxygen here and let them reactions to produce the water and some electricity. So if you look at this figure, you cannot be figured out how it's working. So I will show you in the next slide. So this is a chemical reaction of the fuel cell. As you see, we have the anode side and cathode side. So in the anode, we actually use the hydrogens that will be converted into the proton and electron, and in the cathode side, we will supply the oxygen, and then the oxygen will receive the proton and electron to produce the water and some heat. So the overall of the reaction would be hydrogen part half oxygen to produce the water and some heat. Okay, then when they get this one, so we will figure out how it's working. So this is a animation figure about the fuel cell stack. So as you see, we have the anode side and the cathode side. In the anode side, hydrogen will be filled up into the anode side and separate onto the green one and yellow one. That the green is a proton and the yellow is an electron. And electron will be moving on to the current as a current that we will get some electricity from them, and then the green one or the proton will be moved along to the membrane and will be collect together in the cathode side and react with the oxygen on the cathode side to produce the water and some heat. Okay. In my research, I focused on proton exchange membrane fuel cell or PM fuel cells because the catalyst of PM fuel cell actually is a platinum, and the reaction zone was limited within the interface between catalytic layer and the ion conduction membranes. So this is a catalytic of PM fuel cell. So we will operating at around 50 to 110 degrees Celsius, and the Natthakorn is used as a membrane, and we use the fuel is a hydrogen and the oxygen is the air or the oxygen. So this figure is show you about the structure of PM fuel cell. So we will have the MEA or this one, this membrane that we will spray the platinum on it, and then we will assemble it with the artificial layer and cat gas, and then we will assemble with the flow box channel, current collector, and anode and cathode field inlet. So then I would like to move on into my methods, and I will show some operating and condition in this part. So in my experiment, I used the storage geometry of hydrogen and air is 1.2 and 3, and the membrane I use the Natthakorn 211, and the ratio of Natthakorn per carbon is 0.5 per 1, and the platinum loading on the anode side is fixed on 0.1 milligram per square centimeter by using CCM processes. What is the CCM? So I will tell you in the next slide. Okay, the oxygen and the hydrogens we use are fuels, and we will repeat the experiment of the previous student by using the chloride and the additive. So this one is the CCM processes. The CCM processes we will use at spray machines. So here we will put on the catalyst, the catalyst inks here, and then use the ultrasonic here to spray the membrane, to spray platinum to the membrane. So this figure will show you about after spray the platinum loading. This one is a figure of the membrane Natthakorn 211 by spraying with the platinum loading on the anode side at 0.1 milligram per square centimeter, and platinum loading on the cathode side is 0.5 milligrams per square centimeter. As you see, the back one here is the platinum that we spray into the membrane. Okay, and then in next experiment we will test the performance test. The performance test we will measurement the conventional platinum per carbon MBAs with activated at a cell temperature. In my research, I set the cell temperature at 60 and 70 degrees Celsius for 3 hours, and with the air and hydrogen humidification also carry out at this temperature. The hydrogen per air stoichiometry we use at, we say, 1.2 per T respectively, and test at the atmospheric pressure. The active area we use the single cell is around 5 times 5 centimeter or 25 square centimeter. So in activated processes, this is a machine that we use to activate the cell. The membrane is assembled with another equipment and connected with the anode and cathode fields. As you see here, this one and this one is an anode field and a cathode field. So as you see in this box, so it is a structure of MEL. It is structure of the fuel cell that I showed you in the previous slide here. Okay, and about the testing processes, we use the humidification temperature test around 30 to 70 degrees Celsius by varying, and the cell temperature is around 60 to 70. And then this we vary about the carbon paper, or it's called the artificial layer, that all these type. The first one will be HGL 28 BC and HGL 29 BC, HGL 38 BC, NISI 007 and TDL 260, something like this. Okay, and Natthakorn ratio optimizations, we use this condition or this ratio for testing the performance and find the optimum ratio. At the first one, we use the Natthakorn 0.5 per carbon 1, Natthakorn 0.6, Natthakorn 0.7, Natthakorn 0.8, and Natthakorn 0.9 per carbon 1. And then we optimization of the cathode catalytic loading by fix the catalytic loading on the anode side at 0.1 milligram platinum per square centimeter and vary the catalytic loading on the cathode side as shown in this table. So we vary into the 0.3, 0.5, 0.7 and 1. This one is all the type of the sample that we would like to do the experiment. Okay, and the optimum ratio of the hygroscopic agent of the zeolite. We use the zeolite as a hygroscopic agent to improve the performance of the low temperature fuel cell by adding on the anode side. The zeolite can be improving the water absorption, ion exchange rate, and some thermal stability of the membrane. So this effect will be improve our performance of the membrane. So we vary the zeolite as a 0.1, 0.3, and 0.5 per 1 carbon. And then this is a last part that if we get the best result, we will test it into the long-term voltage decay test by using the dihydrogen and humidification air to test the performance of the fuel cell. The humidification condition of the air is determined according to the average monthly temperature and the humidification. So the test time is continued according to the voltage decay for 120 hours and measure its current impedance every 24 hours. And this is my result. This is some result of my research. So the case one that I say we use the stoichiometry of the hydrogen per air is 1.2 per 3, and this case we use the membrane is a Natthakorn 211 and the GDL is the GDL 260. The cell temperature was set onto the 60 degrees Celsius and the both cathode and anode humidifier temperature are 50 degrees Celsius. Okay, and this is a result of the activated cell. So the left hand side of the graph will be the cell voltage and the right hand side it will be power density and the x-axis will be the current density. As our expectations, this result is not good enough for being it applied with the machine or applied with some device. So we try to do again by changing the membrane from Natthakorn 211 to membrane come from NSYU. So we got this one at a low data of 50 degrees Celsius and 60 degrees Celsius. So we will see at the 60 degrees Celsius. When we compare with our membrane, the NSYU membrane is quite low performance than Natthakorn 211. So we find the problem and we discussing it that when we activated the program, the voltage was not rising up on time that it should be. Probability of this problem is maybe the membrane was cracked due on the GDL are sharp, and when we spraying the membrane from an NSYU, spraying temperature is 80 degrees Celsius, but the membrane came dilated and twist. Maybe the pad temperature will be not enough to evaporation or the solution. So in the this one in the part of the conclusions, the membrane crack or twist that cause to get a bad efficiency or bad result. So you must be careful when we spray the platinum to the catalyst. And the temperature during spray should be suitable with the membrane for preventing the effective with the membrane, so that it will be cracked or twist or it will be pumping. And the PT loading should be changed to a various amount for observing the best results. The performance of this result that I showed you in the previous slide still not our expected, so we need to change some conditions to optimum the best results. Okay, thank you for your attention, and this one is some part of my project. Okay, if you have any question, you can ask me or text me by the Gmails or